Okay, so number 49. We are given this guy. So we want to find the power series representation for the integral of p of x dx. So I think this kind of builds off of the last ones. It's whatever you think is the best form given your setup. So we are going to need to take the integral. We could take the integral now, or we could take the integral once we find the series, because as we've found, taking the integrals and derivatives of series aren't normally that crazy because it's normally related to the power rule. But if we look at the integral of ln doesn't go away. It's not like we take the derivative and it turns into a fraction. So this actually comes from knowing another set Maclaurin series for our ln function. So actually, ln of 1 plus x equals the sum as n equals 1 to infinity times negative 1 to the n minus 1 x to the n over n. And in our last problems, it doesn't matter if this is squared, because I could just plug in x squared instead of x. So that's all I'm going to do. And then I'll use this because this is just x to a power, and then I'll integrate once it's actually set up as a power series. So I'll say only thing that's going to change is my x, and that's just going to turn into x squared. So I'll say n equals 1, negative 1 to the n minus 1, x squared to the n over n. And this ends up being, and I'll need to take the derivative of this, or integral of this, x to the 2n over n. All I need to do to take the integral is just add 1 and divide by that. So I'll say, again, negative 1 to the n minus 1 is just a constant. So this will be x to the 2n plus 1 over n's going to just stay there, and we're also going to divide by 2n plus 1 in our denominator. And that's it. So it honestly looks like a really funky problem, but in the sense of writing, not too bad. Let me know if we're struggling with that one at all. But it's just knowing this guy. If you can't bring a formula sheet, I apologize. And that's tough. I don't think she'll throw it at you, but I'm not sure what kind of test giver she is in that sense. All right. But just for the sake of time, just because you had me go through a lot of problems, which is fine, I appreciate it. But I'm going to skip over number 53 because you didn't seem like you were struggling with that when we were going through it in our tutoring sessions. So I'm going to skip over it. If you really need it, let me know and I can do another video later on and provide it. But it's just taking the derivative and plugging in your value of a, and I mean, I can send you a picture of it, but you do have access to those solutions as well. So just let me know and we can adjust, but I'm just going to skip over that one for the sake of time. And I'm going to go to our parametric problems because those are ones that we haven't really worked through together. So I kind of figured that that's where we should allocate our time. So we have x equals sine of t, and then we have y equals cosecant of t, and this is from 0 to pi over 2. Let me look this up. This is number 55. Find the Cartesian equation for the curve. Cartesian basically just means standard. These are split up as functions of t, but if we look, if we know cosecant is actually just going to be 1 over sine. And since I have sine here, sine of t, then I could just plug that in. So I can actually very simply convert this as y equals 1 over x in our standard form that we would expect to see these equations to be written in. Sound good? All right, so it says sketch the curve and indicate with an arrow the direction in which the curve is traced as t increases. So we could just plug in some values. I'm not going to go through that, but if you plug in values like this is from 0 onward, so you could just plug in a half to, you know what I mean? You would get, if you plug in any value that's less than 1, you're actually going to get a really small number because to divide by a fraction, you need to multiply by the reciprocal. So this, if you plugged in 1/2, it would actually be 2. And then if you plugged in 1, that would be 1. And then if you plugged in a bigger number, since it's a fraction, it would be a smaller number. So we actually end up getting a line that looks like this. And that's what our fractions end up looking like in these situations. But we need to figure out, what was the words? Indicate with an arrow the direction in which the curve is traced as t increases. So as time progresses, so what we need to do is all I'm going to do is I'm just going to take the derivative. I'm going to take our derivative of x, just because that's going to be a little bit simpler than cosecant. I know what the derivative of x is. So I'm going to say the derivative of x with respect to time is going to be the derivative of sine, which is cosine of t. Cosine is actually always positive in this interval. Because if we go with our unit circle from 0 to pi over 2, our x values are all going to be positive. So on this interval, it is always going to be positive. So if we remember our derivative is our rate of change, so as t increases, x increases. I'm spelling this. You get what I'm saying? As t increases, x increases, because that is our rate of change with respect to time for x. So I believe it asks specifically. Yes, it says specifically as t increases. So she draws arrows like this, indicating that as t increases, this is the direction that we're going. As time progresses, x is getting bigger and bigger and bigger. We're not going the opposite way. If you had a less than 0, it would be the opposite direction. Sound good? Not absolutely crazy. And then set up an integral with respect to x that represents the area under the curve in the first quadrant. So the first quadrant, our bounds are just going to be from 0 pi over 2. This is with respect to x. So we need x values here. We need an a and a b. And we are going to say, whenever we set up our derivatives, if this is, I think, a great way to set up these equations, or integrals, excuse me. Whenever we need to find an integral, normally we have a function of y, or a function y, which equals things in terms of x. So this sometimes is a good way to start these equations. And at the end of the day, we need to just remember that all of our terms are d whatever, our bounds, and our actual terms in here, our variables, all need to match whatever variable they may end up being, but they all need to match. So if we just start, we need to take this with respect to x. This is what we're taking it with respect to x. I know that y equals 1 over x. So I can actually write this as 1 over x dx. That's not too bad. And then what I need to do is my bounds are going to be x values. So I'm going to plug in my bounds in my t, because this is going to be my first quadrant from 0 to pi over 2. It's my first quadrant in my unit circle. So I'm going to plug in 0. Sine of t, what's the sine of 0? 0. And then I'm going to plug in pi over 2. What's the sign of pi over 2? It's our y value. That's going to be 1. So this is actually going to be our integral from 0 to 1. Those are x values. That's how we found them. And then of 1 over x with respect to x, or dx. Does this say evaluate? Set up an integral. She does not say evaluate. So I'm not going to evaluate, but we could do that fairly easily if we wanted to. Okie dokie. Only a couple more pages in my notes. And again, just for the sake of time, I may not do all the end problems just because I think the main issue with the last few problems is that there were typos. So I may just send you pictures of my solutions. And then again, if you want, we can go through them like this. But if you feel the need. Okay. So now we're going to do number 56. And number 56. How much time am I at? 11 minutes. So consider very similar setup. X equals t squared minus 2. Y equals 3t minus t squared. And I think I need to turn on some lights in here because it's getting dark. Okay, so find dy dx. So this, I think, was all the way back in Calc 1, if I'm not mistaken. So a little bit of some fundamental stuff. Dy dx. I don't have y with respect to x, but I have a y that I could take the derivative with respect to t. And then I also have an x that I could take the derivative with respect to t. And again, this is why notation is important because it helps us do stuff like this. And this is a complex fraction, so if I do this, I would have dy over dt times the reciprocal, which is dt over dx. Our dt's would end up canceling. So that is why I can take the derivative of y with respect to t and divide it by the derivative of x with respect to t, and that is going to give me my derivative of y with respect to x. Not too bad. So I can find dy dt. That's going to be 3 minus 2t. And then dx with respect to t equals 2t. Yep. So this is actually going to be dy dx is going to be 3t, or 3 minus 2t over 2t. Not too bad. All right. Find the equation line for the tangent line to the curve at point xy. -1, 2. So this is my derivative. So what I can do is I can find what my slope is at this point. I don't have any x's and y's in here. I just have t's. So what I can do is I can plug in my x into this equation and get a t, and I can plug in my y into this equation and get a t, and hopefully one will match each other. So if I do -1 squared minus 2, so it's going to be 1 minus 2 or -1, right? I think so. Oh, I'm doing this wrong. This is my x value. I need to set it equal to this and solve. So I'll say -1 equals t squared minus 2. There we go. And then if I add 2 to both sides, I'm going to get +1 equals t squared. And then t is going to equal positive or -1. But I'm pretty sure we were given an interval in this, and I did not write it down. Yes, this is actually just on the interval. 0 is less than or equal to t, which is less than or equal to 3. So we actually aren't in the interval if I say -1. So I'm just going to ignore the -1 because it's not going to matter for our interval in this specific problem. All right. And then I'm going to do the same thing for our y. I'm going to set our y value as 2, and then I'm going to solve for that. And I'm going to say 3t minus t. I can factor out a t. Set both of these equal to 2, so t equals 2, and t would also equal 3 minus t, 3 minus t would equal 2, and then if we were to solve that, 3 minus t equals 2, add t to both sides, subtract 2 from both sides, t would also equal 1. So here, at this point, the only matching value for my time is 1. So my point in time where we are at this x and y coordinate is going to be 1. That is how we find what value at time that we need to find our tangent line for. Because I have my rate of change, so to find my slope, then I need my time 1 and plug this into my rate of change formula. So my rate of change is going to equal my slope, which is going to be the equation of that line. I believe we need to write the equation of the line. If not, that's a little bit of a waste. Yeah, find the equation of the tangent line. So then my slope is going to be 3 minus 2 times 1 over 2 times 1. So that's going to be 3 minus 2 is 1 over 2 equals 1/2. All right. And then I have everything that I need for an equation of a line. I have a point, I have a slope, so I can use my point-slope formula. This will be y minus my point equals m times x minus my point minus -1 is going to be +1. And I could do some algebra, and I believe this will end up being 1/2 x plus 5/2. And that is our tangent line at this point. Right? And then I need to set up the integral of the area enclosed by the x-axis on the curve. All right. So what I need to do is our base integral. Again, I think it's a great starting point. I'm going to set up, normally it's a function with respect to x. That's just what our most common things are. And we actually were given a graph for this. We were given, I'm going to erase this in a second, but we were given 2, 3, 4, 5, 6, 7. Kind of looks like this. So we know she crosses the x-axis at -2 and +7. So my x bounds would actually be from -2 to +7. We could find that if we did more algebra, but I'm not going to. So what I need, since I don't have this with respect to x, I need to enter this with the information that I have, and it is going to end up being with respect to t. I know what y equals with respect to t. Y equals that. So I could say 3t minus t squared. And then I actually know what dx is, because over here, I found dx dt equals 2t. So if I multiplied by dt on both sides, my dx actually equals 2t dt. That's what that equals. Here we are. And then all I need to do is find my bounds. These were x values. So all I need to do is plug these into x to find what my associating y would be. So this would be 7 equals t squared minus 2. Add 2 to both sides. I'll write this out. 7 equals t squared minus 2. Add 2 to both sides. And then that's going to be 9. Take the square root of 9. That is equal to 3. Positive and negative 3, but again, we don't really care about our negatives because it's not on our interval. Same thing for negative 2. I'll say negative 2 equals t squared minus 2. Add 2 to both sides. That would actually equal 0. Square root of 0 is just 0. So my bounds is actually going to be from 0 to 3. And I'm not going to evaluate this, but all you would need to do is just distribute your 2t. That would be 6t squared minus 2t cubed. Do your standard power rule. Nothing funky going on over there. And you would get 1 minus square root of 3 over 2 is what I ended up getting. All right. Moving along. Is that just part 1? No, that was all A, B, C. Guess I didn't label. Oh, that was 56. I'm looking at the wrong one. I never even evaluated that. It doesn't say evaluate it. I was looking at the wrong one. That answer that I gave is not at all the answer for this problem. It's the answer to the next problem. Okay. Apologies if I cause confusion. That is not the answer that you'll get. Okay. So, jumping to number 59. Okie dokie. How many do we have left? Sorry, I shouldn't be recording that. 59. We only have 5 left, and I don't think we'll go through every single one. Okay, so one more parametric curve, it seems. Yes, one more. So this will be okie number 59. This is going to be very similar to the one that we just did. So find the equation of the tangent line. All I need to do is find my derivative of y with respect to x. So I'm going to find the derivative of y with respect to t, find the derivative of x with respect to t, and put the derivative of y with respect to t over the derivative of x with respect to t. So this is going to be my derivative of this. So this 1 will go away. The derivative of sine is cosine, so this would actually be negative cosine t over 1 minus derivative of cosine is negative sine, so this would actually be plus sine of t. So that is going to be my derivative. Not too crazy. And then I want this to be at point t equals pi over 2. Excuse me, pi over 3. So if I plug in that, this will be negative cosine of pi over 3, 1 plus sine of pi over 3. I had to get my unit circle up for this. Do I not still have it up? Oh, yes, I do. Love that. So my cosine of pi over 3 is 1/2. And this is 1 plus sine, which would be 1 plus root 3 over 2. And then if we do a little bit of algebra with this guy, yeah, this would be, she just wanted us to add these two together to get rid of the complex fractions. So this just ended up being, I'm not going to go through the work because we could do 2 over 2 plus this, multiply by the reciprocal, da 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 da. Yeah, and that just leaves us with negative 1 over 2 plus root of 3. And yes, there is a radical in our denominator, but she did not care about that, so I'm certainly not going to radicalize my denominator. So that is our slope. And this one was ever so slightly different. Last time, they gave us the x and y point, and for an equation of a line, all we need is a slope and an x and y point. Here, we just have the t point. So I actually, to get my x and y point, I need to plug in t. So x would equal pi over 3 minus cosine of pi over 3. So this would be minus 1/2. And then my y would end up being 1 minus sine of pi over 3. So that would be 1 minus root 3 over 2. And I'm not going to write this equation of the line just because it's really funky and I'm going to waste space here. But then you would do your point slope formula. You would say y minus this equals m times x, or m times x minus this, and plug in your points. So this is your x point, this is your y point, this is your slope, and that is what you end up plugging into that point slope formula. So it's not a pretty one. It's not cute whatsoever, but that's all we need to do. All right, so then it says, set up an integral that represents the area under the curve between the points pi over 2, 0, and pi plus 1, 1. It says specifically do not evaluate. So did I miss something here? I'm just triple checking with what she wrote. Yep. So if we go with the process that we have been doing, setting it up as our standard y dx, these are our points, our x points, because normally these begin as our x values. All right. Then we know what y is, so we can plug that in. So that would be 1 minus sine t. And then we know what our dx is because this is our dx dt, and then if we multiplied by dt on both sides, dx would equal 1 plus sine t dt. All right. And then we need to do one more thing for our bounds. So these are our x values. So we need to plug these in to find what our t would equal for these guys. So this would be pi plus 1 equals t minus cosine t. Is that what I did? Actually missed this step. Actually, we didn't do that. No. Because that's going to be funky. It's easier. Our points in time should be the same, theoretically. So what I'm going to do here, because it's kind of hard to solve for t when we have it outside of a trig function and inside of a trig function. So what I'm going to do, because at these specific points, I'm just going to plug in the corresponding y value to see what that point in time is, because it should be the same. So I'm going to say y equals 0 equals 1 minus sine of t. And then here, all I need to do is add sine of t to both sides. And here, I basically need to do my inverse sine. So I need to ask, when in this interval is sine 1? Sine is associated with our y values of our unit circle. So from, where's pi to negative pi? I guess technically here. So we need it to be pi over 2. Yes, pi over 2 is in that interval. And then I'm going to do the same thing and say 1 equals negative sine, or 1 minus sine t. Subtract 1 from both sides, so that would equal 0. And then where's our sine? 0. Our sine is actually at pi, negative pi, 2 pi. That is where all of our sines are going to equal 0. So those are actually going to be my bounds for this equation. Pi over 2 and pi. So those are going to be t values. So I have a t, I have a t, I have a t, I have a t, I have a whole bunch of t's. And here, I think she wanted us to solve because this one isn't too bad. Oh no, she doesn't say evaluate. Yep, do not evaluate. But she does FOIL this to show that it's a difference of squares. So it's not too bad. All right. And then now we need to find arc length. I'm going to have to erase this because I'm running out of space. So arc length, our formula, is going to be the square root of, this is actually equivalent to the other arc length formula that we've done previously, but this is just a lot of times easier to set up when you have it as two functions with respect to time, or a third variable. So here, we actually already did all that work to get our endpoints with respect to time, because I believe it's the same interval, if I'm not mistaken. Yes, it's the exact same points. So we actually already found our endpoints, which is going to be pi and pi over 2. So from pi over 2 to pi. And then we actually already have all of the information that we need. It's going to be this, 1 plus sine t, doesn't matter what order because we're adding these together, squared, plus negative cosine t squared dt. I think that's it, if I'm not mistaken. Yeah, she doesn't even square those. So yes, that is just simply plugging it into the formula. You could do the due diligence of working with the old arc length formula because we did do the work of finding dy dx, but I'm pretty sure she wants you to use this more recent formula because it is easier to use. You do have all of the information already. So on that note, I'm going to upload this video and then we'll get through the last couple of problems.